All right, hello everyone, and welcome to Lab 3. This week we are dealing with the idea of a vehicle traveling at a constant speed. So for this experiment, the work again was already done for you. Even if we were actually here in the lab, we would be using a photograph with your data, which will be available to you on Blackboard, to extrapolate all of our distances to determine how far the cart was moving for a consistent time step, okay? So I will post a video of the experiment being done for you. We're just simply using a cart traveling along an air track to eliminate any kind of friction. So this cart is moving at constant velocity. That means that we are going to have the same distance for a same time step regardless of what point we are along this photograph. So we're hoping to see that as we are traveling from dot to dot, each dot was taken at a time step of 0.1 seconds, that our resulting velocities will remain the same, okay? So we're using our theory, again, constant velocity, change in distance over change in time. We're assuming we're starting at a time of 0. We're going to see a linear relationship. Regardless of our distance, we are going to be using the same time step each time. So we will have a data point at each successive 0.1 second, starting from 0, going all the way up to 1.5 seconds. And we're hoping to see this linear trend emerge. This also means that yes, we will be revisiting the concept of LSQ that we learned last week, but let's not get ahead of ourselves. Okay, so based on this photograph, you are going to have a data table. You are going to have 16 different data points. So our N is just denoting which data point we are looking at. So our first data point will be at a time of 0. Then each successive point, you're going up 0.1 seconds. So 0.1, 0.2, 0.3, 0.4, and so on and so forth, all the way up to 1.5. So what you will do, you will take this photograph, either print it up or even on your computer. You are going to line up vertically with each dot and take a reading. So you see this first dot right here. You can use a ruler, you can use a piece of paper. If we were in the lab, we would be using a clear crosshair so that we could have a horizontal and a vertical line that aligns with every single point. Here we do not have those available, but you will do your best to look at each data point and estimate what that distance corresponds to. Okay, so time, we're just going up in succession of 0.1. Distance, you are looking at where the dot lands on the ruler and recording that distance right here in this chart. Okay, so you're going to do that for every single dot that you see on this photograph. So again, we'll have 16 different data points. Once you have recorded each of the subsequent distances, we will be able to calculate our velocities, okay? We are going to use a formula called interval halving, okay? So this might look a little bit complicated, but hopefully I can give you a better explanation as to why we would use this formula. When we're calculating velocities this way, we are looking at the point ahead and the point behind the point that we want to find the velocity at, okay? So let's say we were interested in finding the velocity at that dot right there. If we were to simply take an average of, let's say, the point ahead, so let's say we wanted to find our average velocity by just simply saying, we'll say this is our second step, and this is our first, D2 and D1. if we simply said d2 minus d1 over t2 minus t1, that would actually give us the velocity right here, somewhere in between the 2 points. We're not looking for the velocity here. We're trying to find the exact velocity at each successive point. So in order to do that, we need to look at the points after and before. So that's what this interval halving does. So this average will not work. Instead, using interval halving to find the velocity at our second point, we're saying if we look at the distance at our third point minus the distance at our first point, so by taking that average, we are actually finding the velocity directly at our second point. So we're simply looking at the points surrounding each of these successive dots to find out the velocity at each dot. So we could keep going here, V3, we would be looking at our fourth minus our second. Okay? So because of the nature of this equation, that means at your very first point and your very last point, you will not have an estimate for velocity because you need to have a point on either side to get an accurate reading using this formula. So you will end up with 2 less velocities than you have data points. Okay? I know this formula can seem complicated, but let's break down our denominator for us. So we know that every single time step here represents 0.1 seconds. So let's say 0, 0.1, 0.2, 0.3, 0.4, and so on and so forth. Every single subtraction here, so T3 minus T1 would be 0.2 minus 0. So you're getting 0.2 seconds. T4 minus T2. So our denominator, because we have a uniform time step, is always going to be 0.2 seconds. So we can actually simplify our equation to simply say, we're going to use D for our distances. Okay, so you're looking at the distance ahead of the point you're calculating the velocity at minus the distance below the point where you're calculating the velocity divided by 0.2 seconds. So this denominator will always be 0.2 seconds, okay? So in this data chart, again, let's say we're looking at the velocity right here. You're taking this distance minus this distance to help you get the velocity there, okay? A little bit confusing when you just see it on the page, but hopefully this explanation helps. It's actually, again, quite simple. You're calculating the velocity for each of the time steps, so you're simply just moving down. So again, looking for it here, you're taking the surrounding 2 velocities. So if we were to move down, looking for the velocity right here, it would be this distance minus this distance to get us this velocity. Okay? So again, this is because if we're just looking at, let's say, our second and first to compare those, it's going to give us a velocity somewhere randomly in between the 2 dots. In order to get an accurate velocity at each individual dot, we're averaging the points on either side of it. Okay? So just a basic math equation, distance ahead minus distance below the dot that you're looking to calculate divided by 0.2 seconds. Okay? So we'll have a whole column of velocities, that you then can just use to get your average velocity. Simply again, add all of the velocities together and divide by, so again, you're going to have 2 less velocities than you have data points. So make sure when you're finding this average velocity, you're dividing by the correct number of velocities, okay? So that's how we'll find our average speed. Make sure you're following along step by step with each procedural step. Again, you will have this photograph uploaded to Blackboard. By aligning the crosshair, that just means make sure you are doing a good job of accurately lining up each dot and getting an accurate value of what that distance represents. So you're recording all of these different distances. Then there are additional procedural steps that just ask for something simple like the distance traveled between your 3rd time step and your 6th time step. Do not forget to include these. Again, make sure that you, on your own, as you are going through the lab, check each individual procedural step off. This is as simple as it sounds. So when we're looking at procedural step number 7 on your handout, it's saying calculate the distance traveled from T3 to T6. You simply would be saying this distance would be your 6th distance minus your 3rd distance. It is that simple. Just a basic subtraction problem to see how far the cart traveled between these 2 time steps. Okay? We are going to have 2 graphs in this lab. We will have one associated with our distances. Again, this should look like a straight line. So a linear relationship when we're looking at distance versus time. Then when we look at our velocity, we are saying our velocity is constant. So it should not be changing regardless of time. This results in a horizontal line. Okay? So again, we are going to be doing an LSQ. I will go over that in our next video. You can use the skills you learned last week. You can use the handout from last week, the error analysis packet that's under resources to perform this, but I will post an additional video as well going through the steps of the LSQ. We are not connecting our dots with a straight line. We are finding the equation of the line of best fit using the LSQ method that we learned last week to find this line. Also here, you're plotting all of these individual velocities. Again, it may not be an exact straight line. You're hoping they should be very similar to a horizontal line. But then procedural step 13 asks for you to calculate this area, because again, we are looking to compare a basic subtraction to the area that we would get from our graph. And we are hoping that these 2 values end up about equal. That from our graph, the area would give us the distance it traveled, just as this basic D6 minus D3 gives us the exact amount it traveled in that time. Okay? In order to find the area of a rectangle, again, you are looking at just a basic algebra equation. You are multiplying this height, which would be your distance from 0 to V0, by your length, okay? And again, you are looking at the change in time step from 0.2 seconds to 0.5 seconds. So this is just your 0.3 seconds, okay? So you will end up getting this V0 value, and you will be easily able to, again, perform this basic arithmetic to find A, to then be able to compare it to D in your error analysis. So that handles all of our procedural steps. Again, make sure you are going step by step through each procedural obligation that you have to make sure that you have all of the relevant data needed to complete this week's lab. And I cannot stress enough how important it is to look over your lab report format sheet when performing your lab reports each week to make sure that every section is accounted for. Okay, we will move on to the error analysis.